Okay. So in the last session, we saw the dependence of L and R. That means basically we saw that how the resistance, basically the output resistance would vary depending on how we change the length. So now here we'll today continue with that exercise and we'll continue to build what is known as current source or what is known as current mirror, keeping aside all the objectives what we have designed till date, and we'll try to obtain a proper current source with the help of a simple MOSFET. So we saw that I also told that with a proper W equal to 10 micrometer, we try to vary certain L values. We did that variations and we figured out that for a particular value of L, like for example, when we considered uh, L of 10 micro and W was also fixed to 10 micro, we saw that it becomes the ratio of 10 by 10, which is 1. And we could observe that the maximum resistance, the output resistance, what we were getting was 1.14 mega ohms. Now, I also asked you, or basically, I also told that it doesn't mean that a ratio of 1 would fetch you a same output resistance. Like basically, let us try to verify that quickly. So here now, let us try to figure out to meet up three objectives. So objectives for today's discussion or lab sessions would be, first one, to fix W by L ratios and verify dependency of R out on L. This we have done it, but we'll elaborate it and figure out how we can vary the L and fix a particular value of, or how we can vary the R and sorry, how we vary the L and fix up the R. And the second objective is to fix R out of a current mirror. In fact, before that, we need to build the current mirror. We'll build that and then we'll fix up that. And third is to find I out, output current, which we are going to generate from the current mirror. And then finally, we'll also see the region of operation of that particular current mirror. What exactly I mean by region of operation is basically whether that particular MOSFET which we are using for current mirror, whether that is present in the linear region, saturation region, or in the cutoff region. So all these understanding will try to gain some insights onto this. Fine. So first, well, let's fix up and figure out the W by L ratio first for a particular MOSFET, and that particular MOSFET we will try to use it in our entire exercise. So let's go to this cadence tool. I'll just new cell view. Anyhow, we did that exercise, right? So I'll just open up that NMOS length calculation thing only. Yeah. So we have this particular MOSFET. So what is the agenda here is basically I'm using a simple AC source over here through which some voltage is applied, and then whatever the current is generated, based on that I'll be getting the R, and that R is directly dependent on my your L here. So here, since I'm putting my L as a parameter as capital L. So let us try to launch ADL, get the L from the cell view. Okay, let us try to fix up L equal to 1 micro. And now what is the W here? I also try to change the W. Just want to show you if W here you have to change the finger width. Then automatically total width will change. The number of fingers is 1. So 1 micro multiplied with 1 will be total width will be 1. I'll talk about the finger sometime later. But right now, whatever changes you have to do it in the finger width here in this position. So now W is 1 and we are keeping, if you see, L is also 1. So basically that means the ratio is 1 by 1. Now for this 1 by 1 ratio, let us try to do the analysis. Vary it from 1 to 100 megahertz. And then let us try to plot the current. This will be my drain current. Press escape. And then go to the window over here. Run it. So this is the ID versus VDS graph in terms of frequency. I'll take the reciprocal of that by sending it to the calculator. Here is my 1 by X. Once I do that, whatever the value I'm going to get, that will be my resistance, which I am getting it as 365.4 kilo ohms. So let's try to make a note of it. So for the first one, if W is 1 micro, L is 1 micro, R out, I am getting it as 365.4 kilo ohm. Now what happens if W is 10 micro, L is 10 micro? Maybe I'll just take up one more things, 5 and 5. I'm just trying to give you an idea, fair enough idea, that ratio of 1 for various values of W and L doesn't mean that your R will also have a similar value. So let's minimize this. So let's change the L to 5 micro, and I'll also change this W to 5 micro so that my ratio again becomes 1. Check and save it. Now if you see, W is 5, I have kept it already, L I am wearing it as 5. So again, everything is set. I'll just window and I'll run it. We'll repeat it, send it to the calculator, take its 1 by X value, run it. Now if you see, it has become 821.25. That is 821.25 kilo ohm. That means straight away R out increased. Now let us try to even see, like for example, we'll consider this case only. If W is 1 micro and L become 5 micro, will that have a dependency and will that reach somewhere over here? Let's try to look into that. So let's try to minimize this. I'll just try to make W as 1 micro only, but this time I'm making it as L as 5. So the ratio is obviously W by L is 1 by 5, right? W is 1, L is 5. Why I'm doing, just want to understand, if L is just increased, keeping W as same, what value it is going to have. Then we'll send it to the calculator. Take 1 over X. You're getting 4.036, almost 4 mega ohm. See over here how wonderful it is varying. Now I'm getting R out as 4 mega ohm. That means let's tabulate it. If W equal to I'm fixing it as 1 micro. L I change it to 1. And the moment I kept W as constant, I changed L as 5 micro from 1 to 5. My R out suddenly increased from kilo ohm to mega ohm. Isn't it interesting? Now see, that's what I was telling. It is the always the variation of L that will define the final outcome, that is defining the R out. So I can here what was the scenario? I just wanted to understand. I am varying both the W as well as L. L of course was 5, but on top of that W also varied. That means your ratio become again less. Here if you see what is the basically the dependency, R is directly proportional to L, or basically it becomes L by W, or it depends on basically L, the inverse of W by L, the inverse of aspect ratio. So here the W by L ratio was 1. Here in my this present case where W is 1, L is 5, the ratio become 5 because 5 by L is 5 by 1 is 5. So the ratio drastically increased. So that's why R out increased. Now that's what, if you keep W as constant and keep on varying L, obviously R out is going to increase. So now we saw that I made it as 5 micro and L also equal to 5 micro. That's when I got it as 821.25 kilo, because here again the ratio become 1. Now let us try to fix W as 5 and then vary L from 5 to 10 micro. Let's try to see this, what is going to happen. Keep W as 5. Let's save it. I'll try to vary L to 10. Basically, I'm making L by W as, that is 10 by 5. L I'm keeping it as 10, W as 5. Let's try to run it and send it to the calculator, and we'll take 1 over x of this. If you observe, it is even better. It is getting 2.27 mega ohm. So that means here 2.27 mega ohm, right? So look at the things. Now finally we'll keep 10 micro and L equal to 10 micro. We'll see this one, and also we'll change L to 20 micro. Obviously here the value will be more. Now see, the ratio here was L by W was 5. That's why it was even more. Whereas here, though L became 10 micro, which is greater than 5 micro, but on top of that, your W is also varied. So that means L by W became only 2. And that's why your resistance is somewhat lesser than the 4 mega ohm for which you are getting earlier. So now for this particular case, L is 10 and W is 10. That means the ratio is 1 here. Let's try to see what is going to happen. Both 10. Let's try to look for that. So in the schematic, I'll change it to 10. In fact, I can, to do this sort of experiments, I can even, let's do that. I can even change the parametric value of W to W, and both W and L I have mentioned as parameter. Let's try to look into that, whether will I be able to achieve that, and I'll bring both. Yeah, so here only. So what was my intention here? To obtain both L and W as 10. Here only I can keep on giving the value. So let's turn to calculator. If you see, it's lesser because the ratio has become 1, 1.14 mega. So So I'm seeing it as 1.14 mega. See, now simple question. See, if you see, or simple observation, the ratio here was 1. The resistance was in terms of kilo. The ratio here was also 1. It increased because L has increased, and that's why the resistance, if you can see the increase in resistance, but it is not that encouraging as compared to your other value of L. The core objective or intention here to observe is, even though the L by W ratio is 1, the R value is kept on changing. Even here also, W by L ratio or L by W ratio is 1, but it is changing. Now, we have to choose appropriately what particular combination of L for a fixed value of W, because here we are not going to vary W. It's not that we keep on varying W, because R is mainly dependent on L. We'll fix up W in the sense R is inversely proportional to W but directly proportional to L. So we will try to fix up the W, and we'll try to vary L, so that the moment we keep on increasing the L, we'll see that resistance also increases. See, now if you also see here, the other way, basically here I kept on increasing the W, right? But see, we'll do other way around. Here what we did, I increased W as well as L. So we'll try to now do it other way around. We'll have one more case study. We'll try to do that. We'll fix up W as 5 micro and L as 1 micro. This combination we haven't tried, right? So I'm just increasing W, but I'm keeping L as minimal, or rather to ensure more combination, I'll take up this value. I'll keep W as 10 micro. I'll do other case study, and then L is small, and again 10 micro, L is 2 micro, 10 micro, L is 5 micro, and then we anyhow know L is 10 and W is 10. We have this one. So we'll try to decrease the value of W. Sorry, decrease the value of that means I'm just trying to make sure that the value of L is smaller than W. Let's try to do that. So that one combination, and other than that, we'll also try to see these combinations as well, W and L. So what I'll do, I'll keep on decreasing W from 10, 5, 1, and this time I'll keep L as 10. Anyhow, this we know that. So maybe we'll have one more combination. Yeah. So this we have already figured out, which is 10 and 10. We get it as 1.14 mega. So let's try to do this one rather than this combination. So we are just decreasing the W, and we'll keep L as constant. And then here in the other case, we'll try to fix up L as again, L as constant. I just want to show you the dependency of both W and L as constant again. Now here I decrease the W. Now here we'll try to increase the W. And both are the same, either this way or that way. We'll get the same result only. Let's try to do that. Let us first L as 10 and W as 5. L as 10 and W as 5. Basically, here I think we have done with this combination here. L as 10 and W as 5. Yeah, we have this combination also, right? We have already done this one. L as 10 and W as 5, which is over here. We're getting it as 2.27 mega. And then we tried L as 10 and W as 2, not. We'll do this one. L10 and W2. Change it here directly. Let's revalidate it. I'm just closing the calculator. Yeah. If you see, anyhow, the value of W is very, very large as compared to W. So obviously, we are supposed to get a larger value of resistance. How much large? Let's see. 5.64 mega ohm. So I'm seeing here. Okay. Then we'll keep L as 10 and W as 1. I think this is being done. Not yet. Let's do that. L10 and W as 1. If you observe here, in all the cases, we have to observe the ratio or dependency of R to L. L is obviously more as compared to W here. So obviously, we are supposed to get more and more resistance. Let's do that. 11 mega ohms. You see the combination where you are, see, I said I am fixing up L, but indirectly, what is that? I am just increasing the L by W ratio. My W kept on decreasing because R is inversely proportional to W. If you see, if W keeps on decreasing, R is going to increase, and you can see over here. So that is the main objective of this. If W decreases, R out increases, right? So this is one of the observation. So other way around, what we tried over here, if we just see over here, where let us try to fix up the W. We did here haphazardly for all the combination. Let us try to do here. Now again, and on a quick go. Now I am going to fix W as 10. I'm going to vary L. I'm going to vary from 1, 2, 5, and then I think we have done all these combinations. Let's get the outcomes what we have taken over here. So for W equal to 10, L equal to 1, we I think done. W equal to 1, we have not done that. Let's do that. W equal to 10 micro and L equal to 1 micro. Equal to 1 micro. So my expression is here. W is 10, L is 1, W is 10, L is 1. Here I am just fixing W. Okay, so let us try to evaluate that expression. Send to calculator, get that to the function, take the inverse of that. We will be getting 36.8 kilo ohms. 36.8 kilo ohms. Here in the fix L equal to constant. That's what we did here. Here fix W is equal to constant. Okay, let's now increase the L. I'm fixing up only W. W is being written as 1 only. So now increase the, yeah, W is what? W has been written as 10 and L I'm increasing to 2. Yeah. Increase it to 2. Now, obviously, if you observe, what should be the scenario? Let us try to do that. Here, L is now increased, W is being fixed. So now let us see what is that. I'm going to get it over here. It's 103 kilo ohms. Obviously, my resistance should be increased. See, and it is increasing because L is increasing, right? See, either you decrease W, fix up L, or you increase L, fix up W. In either cases, it is going to work. Same here. L is directly proportional to L by W. That means if L increases, again R out increases. So I think W is 10, L is 5. We might have done over here. W is 10. We have not done that. Okay. 10 and 10 we have done. Both 10 and 10, 1.14 mega, that we can mention over here. 1.14 mega. W is 10, L is 5. Let's try to do it one last time. And then finally we have to fix up that those particular value of W by L. So L, I'll increase it to 5. So once I do that, again I'll send it to the calculator. Take the inverse of that. 411 kilo ohms. Obviously, it has to be more than the previous value. So we have to conclude that either you increase L. It's a wonderful observational experiment where we figured out the dependency of R out on your L and W. Either you increase the length or you decrease the width. And when you do both of them, you keep any one of them constant. Do not do both increasing of L and W. It is not going to help you out in achieving the proper value. Now, among these, let us try to fix up the one which is going to have a maximum value of resistance. Now, I feel for W equal to 1 micro and L equal to 10 micro, through our entire experiments, we can see that this is the particular value where I can see a maximum output resistance of 11 mega ohm, which is definitely going to fetch me a wonderful results in terms of the various applications. So that's why I'm going to choose henceforth my W equal to 1 micrometer and L equal to 10 micrometer as my value. Either you choose this one, or if you want to make your ratios to be easily accessible, if you want to ensure that the WL ratio, whatever you say, it should be easily remembered when you want to have a similar value, or you have to have some finite rounded figure number, you can choose any other values, something like this. Even W equal to 10 and L equal to 10 is also fair enough because you're getting in terms of mega ohms. Yeah, so that also can be done, or you can choose any value among these things you can choose. So these are the some of the values that you can choose. So let us try to fix up these value, W as 1 micro and L as 10 micro and henceforth, so that we can have fair enough. If I say W by L ratio would be 1 by 10, the ratio would be 0.11. Or if I change, if I want to observe what is my L by W ratio, it would be 10 by 1, which is equal to 10. So even here also it is easy to remember. So that's what is my first objective, to fix up WL ratios and verify the dependency of R out on RL. Okay. So this is all about this particular thing. And then now we'll try to build the current mirror, and we'll see, we'll build the current mirror and we'll see, we'll fix up that particular R out. So basically to fix up R out means we have to fix up that particular MOSFET will be having this ratio, W as 1 and L as 10 micro. So we can do that, or we can do the other way around also. So where we have seen, see here I showed you that basically how you can ensure that you get a maximum R out of by variation by varying your L and W. So it's not that you fix up this only. We can fix up any other values which is going to fetch me a good amount of resistance. So if I just fix up this also, where W is 10 micro and L is 1. So even here also, see, any resistance which is in terms of kilo ohms or mega ohms is fair enough. See, the only executional dependency, or basically how your entire outcome would change if you change the W by L. We'll also discuss that, because now here we observed that when we change W and L, how your R out is going to change. Now, if this R out changes, how your other outcomes are reflected, or how your other outcomes are also going to change, that also we will try to understand by varying again W by L in our subsequent experiments. So now, basically, you can choose W by L as, let's try to fix up two particular things. One is we'll fix up this one where L is 1 micro and W is 10 micro. We'll fix up this one. Another one is basically we can fix up 10 micro and 10 micro. We can even fix up this one, which is also fetching me a fair enough one of as an aspect ratio. We can do that also. So let's do that. WL equal to 10 micro, and we'll also see other parameters or other outcomes how it is going to vary. So we'll try to look into that also. So for that, we need to first build the current mirror, and we'll try to figure out, basically let's try to do that here. Current mirror. So I'll just try to give you a small glimpse of what exactly we mean by a current mirror. So let us take a simple MOSFET. So basically simple NMOS. The concept of current mirror is to mirror the current that is flowing in one particular wing into the other wing, giving you the same current that is being flowing in the original reference wing. So I'm going to call it as a I reference. Here will be my VDD, and whatever current I'm going to see or hear, that will be my I out. Obviously body will be connected to source, those that I'm not going to consider over here. Okay, let's write it. So it will be like this. So basically this will be my schematic of the current mirror. So when I said fixing up the W by L ratio, so these MOSFETs W by L ratio I'm going to fix up with the value which we figured out just now. So now what is this intent? So if you observe here, the gate of this particular MOSFET, let's say this has M1 and this MOSFET as M2. The gate of M1 and M2 are tied together. That means VGS for M1 is obviously equal to VGS of M2, or VGS1 is equal to VGS2. Let me write that way. VGS1 is equal to VGS2. Now, if you observe here, see basically even the how this particular MOSFET is connected. We have seen that if a MOSFET's drain and gate are connected or tied together, that particular MOSFET is pushed, or basically it is known as a diode connected MOSFET. So M1 is diode connected MOSFET, or basically that particular structure is known as diode connected MOSFET. And this particular diode connected MOSFET is having VD and VGS same. So VG1 and VD1 are same because they are tied together. If that is the case, then if I try to understand the condition for saturation region, so if I see condition for saturation, what is that? VDS should be greater than or equal to VGS minus VT. So now let us consider, let M1 and M2 have same parameters. That means VT1 is equal to VT2 is equal to VT is equal to, let's say, 1 volt. And if I just try to fix up and figure out this condition, now whatever is the voltage of VDS, like if VD is equal to 3 volt, then Vg will also be equal to 3 volt. Now if I substitute this over here, 3 is always greater than 3 minus 1, that is 2. So that means this M1 will be always in saturation region. So based on this condition, M1 will be always in saturation. If M1 is always in saturation and the same gate is, or the same gate voltage is applied to your M2, that means M2 would also be in the saturation region. And if M2 is also in the saturation region, that means the same amount of current that was flowing in M1 would be reflected in M2. So that is the basic concept over here. That's how I say the current in M1, which is my I reference, will be mirrored into M2. So basically the intent here is to say that because M1 is pushed into saturation region and the same gate voltage is applied to M2, and both M1 and M2 are same with respect to other parameters like W by L, mu and Cox, everything, because M1 and M2 are two similar MOSFETs, and because two similar MOSFETs are fetched, are given with the same amount of VGS, and because M1 is already in saturation region, that saturation region current, or the current that is already flowing in M1, which is the current in the saturation region, or basically whatever the current that is flowing over here, will be exactly mirrored into the I out, or basically your I out will be exactly same as that of your I reference, or basically the current that is flowing in M2 will be same to that of M1. So that is basically the concept of current mirror. We will try to rectify and verify this entire observation by building the schematic, and we'll try to see how exactly it is going to mirror, and what is the dependence of your I out on I ref, or basically if I keep on changing my parameters of both MOSFETs, how impact it is going to have on the IOT. So all these things we'll try to understand when we try to address the other two objectives, basically to build the current mirror and to find the I out, basically the output current, which we are going to see over here. And the basic application of this current mirror is to see that I can generate n number of different currents using this reference. See, this is one reference current. I can generate different sets of currents using the same amount of I reference, and by changing W by L. So basically in my entire bigger circuit, or in my entire bigger system, I can generate different sorts of current by using the one reference current and one MOSFET over here.